Welcome everyone to Calculus 2. We're going to be getting into Chapter 1, Integration over here. And I'm not really going to say anything about that today. Not at all. We mentioned the I word in a future video, but that's where we're at. But what I really care about is Section 1.1. We're going to talk about approximating areas, okay? So we're going all the way back to geometry. Sort of, with some little twists. All right. So, and we're going to start by talking about a notation. So we'll give a little brief overview of what we're trying to do in this chapter, in this section, and then we'll really get into the summation notation as well. I want to show you why we're doing what we're about to do. So let's just dive right into it. So here's our goal. Our goal is to find this area under a curve. So let's say that, we have some kind of graph. Is that a straight line? Well, it is a straight line. I was really wondering, is it a vertical line? Let's say we have some kind of curve, and maybe the curve looks like this, and we're curious, and we're saying, all right, what's the area under the curve between these two sections? How can we find this area underneath that curve? That's our goal. Why do we want to do that? I don't want to spoil it for you. But there are a lot of reasons why. In fact, we'll spend most of chapter 3, I forget which chapter. We're going to spend about a chapter answering that question, but not yet. And so what we're going to do is we can approximate this area with a bunch of little areas, okay? We're going to divide this into pieces. This is how we're going to achieve our goal. Divide into pieces. So, maybe... we use blue, we can say, well, right off the bat, I can find this blue area really easily, right? This blue area is just a rectangle. Well, that's easy. And then we can just divide it a little bit more, like maybe another rectangle here. There's a little left over, but maybe another rectangle here and another rectangle here. And if we divide this into a bunch of really small pieces, then we can get really close to the area. And the smaller and smaller the pieces we divide it into, the better and better the approximation is going to be. Oh, I don't want to spoil it, but there's a little hint of calculus already peeking through if you remember your Calc 1. But even once after we divide it into pieces, there's one more step, and it's to add it all up. And that's where we're starting today. We are starting here in this video, adding it all up. Because if we're adding up a bunch of things, it can be a little tedious to do it like this, right? 1 plus 2 plus 3 plus 4 plus 5 plus ... plus 10 or whatever. This takes a long time. It takes a lot of space. It's not an easy way to write down adding up a whole bunch of things. We eventually want to add up a whole bunch of things. And that's where this notation comes into play. Let's add up a whole bunch of things nicely. Here's how we're going to write this. I'm going to start by giving you an example before the definition. We can write this with a giant capital sigma, the Greek letter. Okay? And we're going to say that we're adding up, because this just means adding up. That's all the giant sigma means. We're adding up a bunch of i's. And you might say, well, Jason, what's I? Good question, Jason. Well, on the bottom, we tell you that I is starting from 1. I starts from 1. That's what this means. And I ends at 10. That's what's adding up. I ends at 10. So if we combine all of this together, this says that we're adding up a bunch of i's. What are the i's? Well, the i's are starting at 1 and ending at 10. So that's where, I is 1, I is 2, I is 3, I is 4, I is 5, etc. And we keep on adding until we get to 10. That's what sigma notation is all about. So let's get closer to a more, not really a definition, but kind of a definition. I don't really like super precise definitions for these videos. The textbook has some really good, precise and long definitions that you can have if you want. I'm going to be focusing more on intuition and understanding in these definitions. And you can always check out the textbooks for more precision here. So what we're going to do for sigma notation, otherwise known as summation notation, is we're just going to have exactly that. We'll write it as the sum from I, and that can be any letter. It doesn't have to be I. It could be J, K, L, M, any letter we want. J and N are also very common. From I equals 1, or again, it could be any number, up until some other number of anything. So this is A sub I. A sub 1 will be one quantity. A sub 2 will be another quantity. And that's just essentially plugging in the first one for I. And then plugging in the second one for I. And then continually plugging in all the rest of them until you get to the last. Essentially what we're doing is plug in I equals 1 right there. Plug in I equals 2. And so on. That's what summation notation is all about. It's just a shorthand. And that shorthand is going to make things a lot easier and not impossible. And I'm a big fan of easy and not impossible myself. That's what we're doing here. Let's do one more example and then we'll close out the video until the next one where we get into some properties and some more complicated problems, as I'm sure you are waiting for. Example number 1. Write the sum of a bunch of 3 raised to the ith power, where I is going to be 1, 2, up to 5, in sigma notation. Sometimes I'll abbreviate it like this. Sigma, I'll just write sigma, the Greek letter. You may have also seen sigma like this. That's a lowercase sigma, whereas this is an uppercase sigma. Fun fact, if there's notation for adding up a bunch of things as sigma, is there a multiplication? Sorry, I spoiled it. Is there notation for multiplying a bunch of things? And the answer is yes. It's very, very similar, just with a capital pi. You'd go from like pi equals 1 to n of a sub I, but we're not doing that. But if you were curious, that's a little bonus free information for you. You don't even have to pay. All right, comes with the cost of tuition or whatever. All right, let's get to it. So write the sum 3 to the I in sigma notation. So we go back and say, what does sigma notation look like? Well, we start with the sum. Where do we start? Where do we end? And what do we put inside? That's what we're going to do. Sum. Where are we starting? Starting at I equals 1. So we write that. Now you could write, right, we finish at 5. You could write I equals 5 at the end, but that's redundant. We already know we're using I. That's why this I goes here, is to tell us, well, what are we actually counting with? Because I said it doesn't have to be an I. So if, for example, you know, we had something like that, I'm not done here, but for example, right, if I had something and I said add from 1 to 5 of 2i plus j, well, now you don't know, are we going from 1 to 5 for I? Or are we going from 1 to 5 for j? Are we doing both? And that's why it's useful to include the I right there. That's why they did it. All right, and then we're just adding up. What are we adding up? We're adding up all the 3 to the i's. So this is 3 raised to the first I. The first I is 1. Plus 3 raised to the second I, which is 2. Plus the third I. Plus the fourth I. Plus the fifth I. That's what this is in sigma notation. You could use a calculator to calculate this. And you could be good to go. I don't want to do this in my head. That'd take a little bit too much of your time. Try to keep these videos as short as possible, but it does not always happen. And the further you go in math, the longer the videos seem to get. Try to find that balance between, I don't want to spend 60 minutes per video, but I want to give you enough examples, right? Let's do one more. Write 1 plus a quarter plus a ninth plus a 16th plus 1 over 25 in sigma notation. So now we're going to go backwards. We say, okay, I see all this. How can I write this in this format? And these can be tricky. These can be pretty tricky. So let's start with the easy part. Okay. I know the answer is going to look like this, and I'm going to choose I. I doesn't have to start from 1. A lot of times it does. A lot of times it starts from 0, 2. But it can start anywhere. And we don't know where we're ending. So this is the easy part. We need to figure out what goes up here, what goes here, and what goes there. And before we do that, let's just try to figure out a pattern. What's happening here? Well, 4 is 2 squared, right? 9, that's 3 squared. Oh, that's 4 squared. That's 5 squared. This guy's the odd one out. Or is it? Right? Could we not write this as 1 divided by 1 squared? 1 divided by 1 squared is still 1. So what's the pattern here? It's always 1 divided by some number squared. It's always 1 divided by some number squared. And notice that some number, that I, starts at 1, and then it goes to 2, and then 3, and then 4, and then 5. I have too many arrows here. Starts at 1, and it goes up to 5. Now, every time you do this with summation notation, you should check your answer and go backwards. See if we get to where we started, right? If we evaluated this, it'd be 1 divided by the first I squared, plus 1 divided by the second I squared, plus 1 divided by the third I squared, plus 1 divided by the fourth I squared, plus 1 divided by the fifth I squared. Is this red thing the same as the original problem? Yep. Great. That's a good way to check your answer. And there we go. That we have it. That's summation notation. We've started on our journey to calculating this area. Still haven't mentioned what integration is. Still haven't mentioned why areas are useful. But by the end of this section, you will have some of the answers. All right, so go ahead and get started on those homework problems, and let me know if you have any questions. Have a great rest of your day, and I'll see you back for the second video.